Hello, everyone, and welcome. My name is Liz Pemper, and I'll be your moderator for today's WJE webinar, Illuminating Light Pole Maintenance. During the next hour, WJE engineers Noah Fehrenbacher and Leah Ruther will discuss the general components of light poles, common failure mechanisms, tips on how to extend the service life of light poles, when replacement is recommended, and design considerations for new or replacement poles. This presentation is copyrighted by Wes Jenny Elstner Associates. And now I'll turn it over to Leah to get us started. Leah?
Great. Thank you, Liz. So as Liz mentioned, we're talking about light poles today. And light poles are probably one of the most universal structures in the world around us, but arguably one of the most overlooked structures. I think we often appreciate the light they provide, but forget about the pole, the connections, the foundation as assets to be maintained and managed. So essentially, our objectives today are to discuss the general components of light poles, the failure mechanisms that often occur with each of those components. We'll talk about maintenance options or recommendations, and then look at some replacement considerations or repair considerations. And all that to say to avoid situations like this, where you have a surprise failure, and we'll get a call, we have to get out, it's urgency to respond to a failure like this. So the hope is we better understand light poles and we understand how to maintain them to avoid failures that you see in these images. So basic light pole components. There are 6 basic light pole components starting from the ground up: the foundation, anchor bolts, the base plate, the weld, the pole, and the luminaire. I'll generally talk about 2 categories of light poles: the commodity poles, which would be like most likely your parking lot poles. Those range in height from about 10 feet to 30 feet, 40 feet. And then high mast lighting, which is a definition in AASHTO, which I'll mention in a moment. And those are poles 55 feet or taller. You'll find them primarily on athletic fields and for transportation. So AASHTO, American Association of State Highway and Transportation Officials, they provide a specification for structural supports for highway signs, luminaires, and traffic signals, primarily for engineers, designers, inspectors, but it does provide some good context for the different components of light poles, as well as relative to inspections or asset management. Again, it's primarily for transportation poles, but it's used for most pole design as well. So typical construction of the foundation. The most common is going to be a cast-in-place reinforced concrete pier. That's the foundation you see in the image on the left. Along with that would be pile foundations. Those are slender, deep foundations. A screw-in helix, which is a galvanized steel foundation, potentially a spread footing, or direct bury, which Noah will mention later. So just for context, in terms of how deep a foundation may get, this is a project I worked on that had 60-foot tall poles, athletic poles, high mast poles, and it referenced the plan for the depth of the foundation, and you can see the depth was between 19 feet and 21 feet. So for context, that's about a third of the pole height. So just, again, providing context for how deep the foundations can be relative to the pole height. So the common failure mechanisms, cracks is going to be one of the most common failures or conditions you'll see. They can range in size, thickness, quantity, length, but not always of structural significance. Usually you can either just repair them, monitor them, and keep it, essentially keep an eye on them. But we do have a heightened sensitivity or heightened concern when they align with anchor bolts. And that's primarily because a lot of pole foundations were designed with smooth J-bolts. And that used an old procedure which did not account for cracked concrete. And when these J-bolts would fail, they'd deform and just pull smooth out of the concrete. So fast forward, we've changed how we design anchor bolts. If you're familiar with ACI, American Concrete Institute, you'll know that as Appendix G. So we've changed how we look at and design anchor bolts, and we do account for cracked concrete. So that doesn't go to say that the thousands or hundreds of thousands of foundations out there that have smooth J-bolts are of immediate concern, especially if we inspect and we don't find cracks that are aligned with anchor bolts or other issues that may affect that bond. But in the event we do find a crack that's aligned with the anchor bolt, usually we recommend either repair or replacement because we can't argue that the bond hasn't been affected. So just to sort of continue that point briefly, AISD, American Institute of Steel Construction has a quote specifically about hook-type anchor rods. They've been extensively used in the past, but however, they have a very limited pull-out strength compared with that of headed rods or threaded rods with a nut for anchorage. So current practice is to use headed rods or threaded rods with a nut for anchorage. So I'll move on from cracks, but that's some context regarding cracks in foundations. Next is falls. Falls are a very common issue with concrete. Again, not always of structural significance. Oftentimes can be repaired in place with common repair methods, patching, adding reinforcing, etc. Next is leaning foundations, usually attributed to poor soil or poor installation. This is a couple of holes we've assessed where we saw that there's leaning, and we did recommend just removal and replacement of these foundations. And then alkali silica reaction, ASR, or also ACR is an issue. Essentially, this is a chemical composition failure within the concrete itself. And it'll present itself like map cracking or like the condition you see in the image here. It's not easily repaired. It can be repaired. Again, for commodity pools, we'll often recommend just replacing the foundation. But if you're talking about larger foundations, bigger pools, more cost to replace, we will consider some repairs, but usually recommend some material testing to understand exactly what's going on before we do that. So the base plate typically serves as the interface between the steel structure and the foundation. It transfers those forces into the bolts and foundation. I've got a little image here to kind of articulate that. Essentially, as wind is applied to the pole, makes the pole want to rotate at the base, and therefore the plate will react against the upper nut and pull on the foundation or the anchor rod, and therefore transfer that load to the foundation. A little bit about the construction of base plates. Obviously, they have holes in them to accommodate the anchor bolts. And I won't get into this table as much, but it is from the AASHTO specification. And I just want to highlight that hole diameters are often oversized intentionally to accommodate those erection tolerances with anchor bolts. So when the foundation gets installed and the anchor bolts get installed, there's some flexibility with when you come in with the pole and the base plate. So along with that, therefore, we often see washers associated with upper nut install, and those also have certain parameters on the design and particular thickness, size, etc. And I make specific mention of this because it ties right into the common failure mechanisms pull through. So in this instance, you can see the base plate had a slotted hole, and then the washer got undersized. So now it's starting to bend, potential for actual pull-through failure of the anchor. So there are some repair options with this. If there's not other distress or issues discovered, then you could probably just replace the washer with something of adequate size and thickness. Likewise, with a condition like this is a lock nut washer, not really recommended for use with light poles or this kind of construction. It's starting to sink into the hole. It's affected the bearing of the upper nut. It's not an ideal application. So likewise, repairing probably an oversized washer after a further evaluation to make sure there's not other subsequent damage that's occurred. So oversized holes, I mentioned the right way to do it, and this is kind of the wrong way to do it. This looks like they got in the field and the base plate either didn't have oversized holes to begin with, or the anchors got set in the wrong location, so they field modified the base plate to install the pole. Probably would require some additional investigation and analysis to understand if it's been the anchor and the load transfer has been affected, but not an ideal situation. So not necessarily a failure mechanism, but just an unideal situation is when we bury the base plate connection, like you see in these images. It prevents inspection, review of the base plate, the connections, the welds, the bolts, and can lead to accelerated distress that we can't see. So just an unideal situation. So I'll move into the welds. Typical construction for welds, it's really the primary connection type for the connection between the base plate and the pole. And the most common is going to be the socket type base plate connection. That's the image you see on the left. It's where there's a hole in the base plate, the tube or pole will pass partially through the base plate, and there'll be a set of welds, one on the top and one on the bottom. Usually we're most focused on the top one because that's the one that's going to see and give us the most distress. Other options for base plate connections, relative to welds, is going to be the full penetration groove weld. That's where you have the base plate is a little, the hole in the base plate's a little undersized, the pole sits on the base plate, and you'll have a backing ring and then a full penetration groove weld. This is primarily for high mass poles, and really just these two types are the most common, but there are other options out there. So common issues with welds, poor quality welds. This can come in all different kinds and shapes and sizes, but in this image you see that there's sort of an incomplete weld, which can affect the distribution of load and maybe lead to some premature distress. Likewise, this one is a non-uniform weld, not an ideal installation and may not be transferring load appropriately, so may require some further evaluation or just increased monitoring. But most importantly with welds is really about weld cracking. Probably the most common issue we see with welds is cracking, and that can be directly attributed to fatigue. So I could probably have a whole presentation on fatigue, but I want to keep it a little high level. Fatigue is primarily associated with cyclical loading. So anytime a structure is going to be subject to cyclical loading, such as a pole that sees wind on a day-to-day basis, we have to design for the fatigue of that. So usually we call those fatigue-sensitive details, in this case, the welds. For frame of reference, we also design for max wind speed. So I sit in Michigan, and our max wind speed is usually 115 miles per hour. But per AASHTO, if you're talking about fatigue and if your structure needs to be designed for fatigue, this provides a range of about 9 miles per hour to 11 miles per hour. That's a pretty day-to-day wind speed that might be, the pole might be subject to, hence the cyclical loading and therefore the fatigue-sensitive detailing. So that's why we tend to see cracking of the welds. It's most prevalent in square poles, and that's primarily because we have a higher stress concentration at the corners, and therefore they're going to be a little more prone to cracking. A circular pole redistributes that load a little more uniformly and is a little less susceptible to cracking. Here's a couple images where you see cracks, especially at the corner of a square pole. So most often the cracks are readily visible, but in the event they aren't, or we want to spend a little more attention on, or pay a little more attention to if there are cracks there, we will use what they call magnetic particle testing. Essentially, this introduces a magnetic field into the material, flux lines flow through the specimen, and they leak out at defects, such as cracks. And we'll add a magnetic particle on top of the material, such as like a red dust usually, and it will be attracted to that defect. And therefore, it'll tell us, yes, there is a crack there, and what is the extent of the crack or the length of the crack. So that's a little on welds. I'm going to transition, one more slide regarding repairs of welds. So again, I know I sound like a broken record, but when there's a significant structural issue with any component on a commodity pole, oftentimes we just recommend replacement because it's going to be less expensive relative to analysis, repairs, etc. But when you start to move into the high mass poles, the bigger poles, the more expensive poles, we do entertain some level of repairs. And this is an example where there was a cracked weld at the base of the pole, and we did some repair analysis, repair design, and then implementation of a repair here. And this would be called like a steel jacket. So some repair options exist when you have cracked welds, primarily for the high mass poles. I'm going to pass it off to Noah, and he's going to talk about anchor bolts.
All right, thanks, Leah. So yeah, I'm going to take on another one of the 6 components, and that being anchor bolts. Anchor bolts are used to attach the pole to the foundation. They come in all different configurations, shapes, and sizes, anywhere from a minimum of 4 anchor bolts, upwards of 8, 10 anchor bolts at some of the taller light poles. Additionally, diameters of the anchor bolts can vary significantly. It can be upwards of 2.5 inches at some of the taller light poles. One differentiator is whether or not the pole is fully grouted underneath the base plate. So those photos on the right, the upper photo shows pole set on leveling nuts. So what typically happens is your anchor bolts are installed into the foundation. The foundation's cast around those anchor bolts. Then leveling nuts are installed, and as the name suggests, those nuts are used to create a nice level surface the pole is set on top of those leveling nuts and plumbed up to make sure it's nice and plumb, and then nuts are installed on the top side to lock that pole in. But there can be an additional step involved whereby grout is installed underneath the base plate, and this provides uniform load transfer from the pole into the foundation. But actually, generally, we recommend that grout not be installed. Simply setting your pole on leveling nuts allows for good drainage and prevents corrosion from forming on the underside of the base plate and anchor bolts, and additionally allows for you to inspect those elements. Common issues that we see with anchor bolts, one being corrosion. So here you can see are a few examples of where bolt covers were removed, and you can see the corrosion that's developed underneath those. So a lot of times bolt covers are installed to, kind of dress up the base of the pole, and they can indeed provide protection to the pole and anchor bolts. But more often than not, what we see is they trap moisture and debris against the pole and the anchor bolts, and they cause more harm than good. So typically we recommend bolt covers not be installed, or if they have been installed, that they be removed. Another thing that can lead to corrosion is debris. So oftentimes that can be from maintenance operations, whereby, say for instance, grass clippings get blown underneath the pole, or oftentimes we'll see animals build nests inside and underneath the pole. And here again, that debris, that organic matter, is trapping moisture against the base and underside of the pole and base plate, and which can accelerate corrosion. Also soil at the base of a pole. So this is an example where the foundation was installed at grade and soil has migrated in and around the base of the pole and anchor bolts, again, leading to accelerated corrosion. So we typically recommend that the foundation extend up above the grade level. Also, spalls, we have touched on this briefly when discussing foundations, but they can be a problem if they exist right adjacent to an anchor bolt. A couple of problems that this can lead to. One being that you're increasing the unbraced length of the anchor bolt. So in extreme scenarios, that can lead to possible buckling and failure of the anchor bolt. Additionally, you're reducing the embedment depth of the anchor bolt, which also reduces capacity. And also, but typically what we find is those spalls are relatively shallow, and those the first two conditions are not typically of a significant concern. But what is of a concern is they create a small depression surrounding that anchor bolt, and that can trap moisture against the anchor bolt and lead to corrosion. So if we see this condition, a simple fix is simply filling that depression with sealant to create a level surface and prevent water from accumulating there. Probably the most significant concern with regard to anchor bolts is fracturing or cracking of those anchor bolts. And cracking anchor bolts can occur for a few different reasons. One of them being fatigue. Like Leah touched on, fatigue is a process by which an element such as an anchor bolt is subjected to hundreds of thousands or even millions of load cycles. And those load cycles can be well below the design strength of the anchor rod itself, but over those hundreds of thousands of or millions of cycles, fatigue cracks can develop. But a anchor bolt that's properly designed should take fatigue into account, so that by the time fatigue cracks do develop, the pole has well exceeded its expected service life. So generally, that's not a concern as long as the anchor rods have been properly designed and they're not corroded or you're not seeing other distress. Also, you can fracture an anchor bolt just by a one-time high wind event if you were to exceed the capacity of the anchor rod. But the only time that I've actually encountered a cracked anchor rod is when there were loose nuts involved. So if you have one or more loose nuts on a pole, now you're allowing that pole to rock in wind loads. And you can imagine that dynamic action impacting the underside of the nut, transfers a significantly higher load to the anchor bolt. So although you're probably not going to fracture the anchor bolt right away, it is going to decrease the fatigue service life of that anchor bolt. So now instead of, millions or hundreds of thousands, maybe that those cracks start to develop after a few thousand or even hundreds of load cycles. Additionally, loose nuts can be a problem because they allow that pole and base plate to move relative to the anchor rods. So this is kind of the picture that's worth 1,000 words. It shows a leveling nut on the underside of a pole, and you can see that leveling nut is quite deformed from that pole rocking back and forth. Additionally, you can see it's actually created a depression in the bottom of the base plate where it's worn into the base plate. But probably most significantly, you can see the threads of the anchor rod here are deformed. And that's of significant concern because now it becomes very difficult to retighten that nut on the top side. And, in order to repair a condition like this, or if there are cracked anchor rods, you're looking at possibly trying to drill in a new anchor rod, which could be very difficult because they have quite deep embedments, possibly trying to couple on to the existing anchor rod and extending it up. But that again can be somewhat costly and require the removal of the pole. And for commodity poles, it's probably most economical just to replace the pole at that point. So that's why it's very important to periodically monitor your nuts and make sure that they're properly tightened. And in fact, when we've encountered loose nuts, the majority of those anchor rods were actually cracked due to the fatigue loads created by rocking of that pole. Also, loose nuts can lead to that pole becoming out of plumb, which increases the loads on the supporting elements. Partially engaged nuts, so it's important to make sure that the nut is fully engaged on the anchor rod to ensure that it has its full design capacity. So moving on to another one of the 6 components, that being the pole itself. So as Leah mentioned, poles are categorized by AASHTO in terms of those that are less than 55 feet and those that are greater than 55 feet in height. Those that are less than 55 feet typically used for parking lots as well as street lights along low-speed roadways. Poles greater than 55 feet in height, those are referred to as high-mast light towers, commonly used for lighting of athletic fields or along high-speed thoroughfares like interstates or highways. One differentiator is that poles less than 55 feet are required to be designed for fatigue, poles greater than 55 feet are required to be designed for fatigue, whereas those less than 55 feet are not required to be designed for fatigue. But that said, we have encountered fatigue cracks in shorter poles. They're most prevalent with square poles. As Leah mentioned, the square poles create stress concentrations at the corners. Additionally, typically what you'll find is the welds at those corners are of poorer quality, which further exacerbates and leads to fatigue cracking. So poles can come in all different shapes and sizes. Commonly, you'll see round or multi-sided poles. Also, you'll see square poles, and as I mentioned, with the square poles that are more susceptible to fatigue cracking. So typically, you're only going to see square poles used for shorter poles, those that are less than 55 feet. You'll see them commonly in parking lots and that type of application, whereas circular and multi-sided poles, those are going to be used more commonly for high-mast light towers. Additionally, commonly you'll see those poles taper over their height. One condition to take into account, particularly with high-mast light towers, is a condition called vortex shedding. So this is a process by which vortices and zones of low pressure form on opposing sides of the pole. And so as the pole moves towards that zone of low pressure, the vortice and low pressure zone form on the opposite side, and this can create a swaying or rocking motion of the pole, which increases the number of fatigue cycles. And one thing that you can do to mitigate this is tapering the pole over its height. Also, fins can be installed to kind of disrupt that airflow, as well as dampers. All different materials are used for poles. Steel is a very common material that we see. Also aluminum, fiberglass, and concrete. Concrete's a little bit less common, but we do come across those on occasion. Some factors to consider with different materials are cost being one. An aluminum pole is going to typically be more expensive than a similar steel pole. Also weight, so fiberglass and aluminum poles, part of their advantage is they're very light as compared to a steel, or in particular as compared to a concrete pole, which is quite heavy. And that reduced weight can help offset, for say an aluminum pole, some of that upfront costs due to lower transportation costs as well as lower installation costs. Fatigue, also something to consider. So aluminum is much more susceptible to fatigue cracking than, say, a steel pole. A concrete pole is probably going to be the most resistant to fatigue cracking. Also corrosion resistant. So one of the things that, one of the advantages of aluminum and fiberglass poles is their corrosion resistance. Whereas something like a steel pole is going to require some type of coating to protect it from the elements. And one of those coatings is just simply a painted coating. This is going to probably be the cheapest option of the different coatings, and but it does come with some additional maintenance costs associated with it, just making sure that the coating is well maintained, that it's not flaking or peeling, and that it's providing proper protection to the pole. Also, weathering steel, although it's not necessarily a coating, it's a process by which chemicals are added to the steel during initial casting. And weathering steel, when it's exposed to the elements and moisture, forms a layer of corrosion on the exterior of the pole. But what's unique about it is that layer of corrosion remains well adhered or bonded to the underlying steel, whereas a typical steel, that corrosion layer would periodically flake off and expose the underlying steel, which leads to section loss. But with weathering steel, because that corrosion is well bonded, it remains intact and provides protection to the underlying steel. You may have seen this on bridge girders on the interstate. It's commonly used in that application. Probably the best form of corrosion protection is hot dip galvanizing. This type of coating is associated with some additional upfront costs, but I would argue that it more than pays for itself in the end based on reduced maintenance costs as well as the increased expected service life of the pole. Direct bury poles, so these are a nice option whereby the pole, as the name suggests, is just directly buried into the ground. It eliminates the foundation, base plate, anchor bolts, and all the maintenance associated with those items. But there are some factors to take into account with direct bury poles that I'll get into in a bit. Also, slip fit connections. So as you can imagine, with high mast light towers that can be 70, 80, even 100 plus feet in height, that would be very difficult to transport in one segment. So typically those are shipped to the site in multiple segments, and then they are connected together on site to form the full height of the pole. And a very easy connection whereby the upper segment of the pole simply slips over the lower segment, and it's just held in place by gravity and friction. They're nice because they don't require any mechanical fasteners. They don't require any welding or any special expertise in order to install them. Appendages, another thing to take into account with poles. So a lot of times we'll see speakers or security cameras installed or supplemental lighting. These may be used for, around, say, an athletic sports field, speakers for announcers or supplemental lighting to light the stands. Oftentimes we'll see banners or signage for the local sports team. If you were at my alma mater, you might see a banner that said, "Go Fighting Engineers." There's nothing that strikes fear into the heart of your opponent quite like a fighting engineer, I assure you. Also, electrical equipment attached to the pole, either to serve that pole itself or adjacent utilities. And it's important to take these appendages into account because they add both wind area and gravity loads to the pole. And typically, those poles are not designed for that additional load. Common issues that we see with poles, one being corrosion. So you can see here's an example of complete section loss at the base of a pole. Commonly, this occurs starting from the inside of the pole working its way out. So if you're not monitoring the interior of the pole, by the time that you observe corrosion, now you've got a pretty costly repair on your hands, whether that be trying to weld on a cover plate or for a commodity pole. Usually it's more economical just to replace the pole at that point. Coating failures, and one thing that can lead to coating failures that I see pretty commonly with high-mast light towers, they often have a safety cable running up to the top for climbing the pole and accessing the luminaires at the top. And if that cable becomes loose or detached, it can wear against the coating, removing it and exposing the underlying steel, and that can lead to corrosion of the pole. Also, improper drainage. So like we talked about with the bolt covers, this bottom left photo shows an example where corrosion, you can see the pitting that's formed in the base of the pole where moisture was trapped against the pole because of that bolt cover being installed. Also, I mentioned some factors to consider with direct bury poles. So this bottom right photo shows looking down a direct bury pole, and at the base, there's water pooled at the base. And that can either be from water that enters the pole from above, if that pole is not completely sealed, or oftentimes, these poles can have quite deep embedment depths, and you can be below the water table. So now that pole can be kept in a constantly wet condition, which leads to accelerated corrosion. And Leah is going to present a case study of some corrosion that she observed on one of the projects she was working on.
Yeah, thanks, Noah. So just a brief example here. We got a call that a pole had fallen on a site. It was a parking lot pole, and we got on site. I'll admit we looked at the poles from the exterior and didn't see a lot of corrosion or issues. So initially we weren't exactly sure what the cause was, but once we did some more investigation, looking closer at the pole base, we actually did some sounding of the pole base. So we tapped on it with a hammer and a nail punch and started poking holes through a number of the poles. And then also coupled that with an inspection on the inside of the pole and basically found our issue. There was extensive corrosion on the inside, making its way out, reducing that cross-section at the base of the pole, and eventually causing some failure of the pole. So we walked away from this one suggesting that they immediately remove about 8 poles because we were able to actively, create holes pretty easily. And then ultimate, suggestion for removal of the remainder of the poles in the near term because they were all exhibiting similar amount of failure. So just an example, corrosion occurs inside out. It's not readily visible. Good idea to check on the inside of your poles just as much on the outside. There may be an issue that you're unaware of, and this was just an example of when that happens. So I'll pass it back to Noah.
All right, so picking up with some other common issues, dents. So AASHTO has some provisions for when a dent can be considered negligible. So if it's below a certain threshold, generally you can discount it and assume that it doesn't significantly affect the capacity of the pole. But if it exceeds those criteria, at that point it is important that a design professional be contacted to evaluate the dent and determine if repairs need to be performed or if the pole needs to be replaced. Also, poles out of plumb, so whether that be because the leveling nuts are not properly leveled or the nuts are loose, that pole can become out of plumb, and that increases the load demands on the supporting elements. So I mentioned the slip fit joints. Some issues or factors to consider with slip fit is you can see in that bottom left photo there, corrosion that's developed in between the upper and lower segments, and that corrosion, as steel corrodes, it expands, which can create hoop stresses in the steel, and that's led to this fracture that you can see on the right-hand side of the photo. And also, although slip fit connections are not particularly prone to fatigue cracking, they do create a discontinuity in the pole. So particularly if there's a flaw already during original fabrication of the pole at that slip fit joint, fatigue cracks can develop at that joint. And that right-hand photo there shows an example of a pole. The upper segment had failed, likely due to fatigue cracks that developed at the slip fit joint. So appendages, as I mentioned, add gravity loads and, more importantly, wind area to the pole. And oftentimes those additional wind loads are not taken into account, and the pole is not reevaluated for those. So it is important that if you plan to add appendages to a pole, that you have the pole looked at and make sure that it can has the sufficient capacity to support those additional loads. Additionally, the connections of the appendages can be an issue. That left-hand photo there, you see just has some light gauge metal straps and kind of a questionable bolt connection there, and some corrosion starting to form on it. So if that connection does detach, that appendage now can become a falling hazard. And also the connection itself can compromise the pole. So on the right-hand photo, you can see there corrosion developing between a strap and the pole, and this can reduce the cross-section of the pole and reduce its capacity. So moving on to the final component, that being the luminaires. So, the whole reason that all these other components exist is to support the lights at the top. And there's a couple of different types of lighting, one being high-intensity discharge or HID lights, another quartz lighting. Both of these are older technologies. They're relatively large and heavy. They're associated with typically higher energy consumption and a limited lifespan of the lights. What we're seeing now a lot is clients switching to light-emitting diode or LED lights. I think we're all probably pretty familiar with these, and many of us have these installed in our home. They're generally lighter and have a lower, what's called effective projected area, or wind area that's subjected, or area that's subjected to wind load. So both of those are good things. You're reducing the load on the pole, but it is still important to have your pole evaluated if you're planning on switching out your lights. They also have a lower energy consumption and a longer lifespan. Common issues with luminaires, I'll just kind of touch on these briefly. They're similar to other conditions that we've discussed with the other components, corrosion, loose connections, either, that luminaire can become displaced and no longer properly directed, or in extreme cases can become detached and become a falling hazard. Also, the support structure to maintain the lights can have, cracked welds or fractured members. So it's important to properly maintain those as well. So switching gears a little bit and talking about engineering inspections. Chapter 16 of AASHTO deals with inspections and reporting of light poles. It classifies those inspections into 5 different categories. Initial inspections, as the name implies, that's an initial inspection used to gather basic information about the pole and the supporting elements and assess its current condition. Routine inspections are periodic inspections performed to assess the current condition of the pole and compare that to prior inspections, whether that was the initial inspection or previous routine inspection. Damage inspection is a one-time unplanned inspection to assess specific damage, whether that may be from a car impact. In-depth inspections, these are close-up, hands-on inspections in which bolt covers and handhole covers are removed, as well as a lot of times it involves non-destructive testing techniques, which I'll get into shortly, as well as interim inspections, which are performed more frequently than your routine inspection, typically done to address because a condition was observed during one of the previous inspections, like corrosion, that you want to monitor on a more frequent basis. So typically we're going to start with a visual inspection for looking for cracks and anchor bolts, and I'll show an example of that. Cracking in the welds, cracked poles, cracking in the foundation. Also looking for loose nuts, whether that's visually loose because it's up, there's a gap between it and the base plate, or oftentimes we'll sound the nut with a hammer, and a tight nut will sound different than a loose nut. Looking for missing or deformed washers, also making sure that the washers are properly sized. Looking for corrosion that may be present, both exterior and interior. So like I said, removing bolt covers and handhole covers to inspect those components which aren't typically visible, making sure that the pole is nice and plumb. So I mentioned anchor bolts. This was an example where we observed loose nuts at an anchor bolt, and the pole was rocking. And I'm going to show a short video here. It's subtle, that you can see fluid moving in and out of that crack at one of the threads there. So that's at a crack location at the anchor rod. And you could see that fluid moving in and out as that crack opened and closed due to the rocking of the pole. But more commonly, the only way you're going to be able to identify a crack in an anchor bolt is using a non-destructive testing technique called ultrasonic testing. And that's a process by which ultrasound waves are sent into an anchor rod, and those waves will bounce off any flaws or cracks in the anchor rod and reflect back up to a transceiver or receiver at the top of the anchor rod, and then an engineer or technician can use a piece of equipment to evaluate that anchor rod, and they can use that to determine depth of the crack as well as its severity, whether it's a partial crack or whether it's completely cracked all the way through. And this was an example of us doing an ultrasonic testing at a pole where we had observed some loose nuts, and like I said, the majority of nuts or poles that we looked at that have loose nuts also were associated with cracked anchor rods as well. So very important to make sure that your nuts are maintained in a tight condition. Corrosion, we'll also use ultrasound to measure remaining thickness of a steel pole. So again, you're sending sound waves through the steel to measure the thickness. And this is a technique we use to evaluate the pole, because we typically cannot get good access to the interior surface of the pole. So this allows us to measure a remaining section of the pole and if there's a significant corrosion present. As Leah mentioned, magnetic particle testing, another non-destructive testing technique used to evaluate, here this is actually yours truly, using magnetic particle testing to inspect a slip fit joint. That green device I'm holding in the bottom photo there is the yoke. That's what's used to introduce the magnetic field into the pole. And that blue bulb I'm holding, I'm using to sprinkle iron powder onto the pole, which will collect at any cracks or defects that may be present in the pole. Luminaires, as I mentioned, clients are oftentimes looking to replace their older HID lights with new LED lights. So as I mentioned, although you're typically reducing the loads on the pole, it is still important to have your pole evaluated because if there's other conditions that are present, like section loss or cracked anchors, that pole may not be adequate to support even the reduced loads of the LED lights. And I'll hand it back over to Leah to talk about asset management.
Yeah, thank you, Noah. So kind of in conjunction with the inspection process, it's reasonable to have a maintenance program, kind of like you would with any type of building. Same goes for a fleet of light poles. So just a mention or an example, this was a site we got out to because they did have a failure. So that's that little red star you see there. And this was a color-coded map that we provided along with some backup information to highlight what kind of poles they had on site and then assign them a category: unsafe, requires repair, monitor repair, or ordinary maintenance. And that was making a play on the ASTM standard for building facade maintenance, repair, and inspection. They provide really nice definitions for each of those categories, and again, creates that baseline now that the owner can use for maintenance as well as future inspections to update and supplement this inspection. So I'll highlight kind of example conditions that we would tag for unsafe. Obviously, major holes or section loss or cracks warranted immediate takedown. If we saw holes in the base plate, like example on the top right, probably requires repair, not of imminent concern, may progress into an imminent concern issue. Some subtle cracking is probably categories such as monitor or repair, kind of in the bottom left. And then obviously if your pole is in good condition, it gets a green and classified as ordinary maintenance. So distressed by the numbers, essentially this is just a conglomerate of inspections we've done in the recent years. This is a 19 sites, and I'd classify it as proactive inspection, meaning where there was no reason, no failure or anything that caused us to get on site other than the client wanting to know what they had. And it likely was probably the first time some of these poles have been inspected since they were installed. And from there, we found that 66 we recommended for immediate removal, 39 were recommended for repair. So that totals to about 105 for repair and replace. So by percentages, 13% for immediate removal, 8% for repair, and about 20% including the total of removal and repair. So just provide some context in terms of what a proactive inspection resulted in. So I'll move into in-house maintenance. A lot of this is going to, be relative to what Noah mentioned in regards to inspection, but a lot of it can be done in-house or by local maintenance personnel. So foundation, looking for those cracks as well as plumbness, and keeping an eye on them in the event they start to advance. Again, anchor bolts and nut, checking for nut engagement, making sure the full height of the nut is engaged on the anchor bolt. And I've highlighted these next two because they're really probably the two takeaways I'd like you guys to take from our presentation day is check and tighten nuts on a regular basis. When they become loose, they can cause subsequent damage to the anchor bolts, resulting in more costly repairs or replacement simply because of a loose nut that could be managed much more easily otherwise. Also removing debris from the inside of the pole. So this leads to advancement of corrosion really quickly, and it's an easy thing to maintain and do on a regular basis to avoid that acceleration of corrosion and potential premature failure of poles or premature replacement. So the base plate, likewise, removing debris from under the base plate, assessing the base plate for proper hole size, washer size, nut bearing. From the welds, if you see a crack, obviously notifying a professional to determine indeed if there's a crack there, the extent of it, if repair options are available. And then the pole itself. So maintaining those coatings to prevent corrosion, inspecting on the interior and exterior, kind of like the case study I mentioned earlier, just taking a peek on the inside to see if there's obvious corrosion. In the event you suspect corrosion or section loss, you could take some thickness measurements to just see if that section loss indeed exists and if it's of structural significance. And then using caution if you're installing appendages. They add load and potentially the pole was not designed for that added load, and also plumbness. So some design recommendations or repair recommendations. If you're going to replace a pole, round tapered poles are more ideal than square poles. Consider galvanizing the poles for increased corrosion resistance or even specifying aluminum poles. Having the welds be done for an automated process has a better result in more uniform, more consistent welds. And then removing or just simply not installing bolt covers to prevent debris buildup, just keeping the ventilation good inside that pole. In the event you do that, it might be reasonable to consider wire cloth screens around the base plate or base of the pole. That'll prevent any sort of nesting animals or bugs that are unwanted inside that pole. And then obviously opting for leveling nuts and supporting the base plate, kind of along the theme of just keeping the pole really well ventilated. So that's the content we have today. I know there's some questions that are rolling in, so we'd be happy to answer those.
All right, thanks, Leah, and thanks, Noah. Okay, let's take our first question. Is there or are there specifications for the frequency of inspection of poles, and is it dependent on the type or service used?
Yeah, so good question. There's no specific requirements for how frequently you do an inspection. Oftentimes, it's going to depend on the type of pole, how tall it is, the conditions that are observed. So, for instance, I mentioned interim inspections. For instance, if we see loose nuts or corrosion, we may recommend that inspections be performed more frequently. But, generally, you're probably going to be looking at, 2 to 5 years between inspections. But like I said, that could be quite variable.
Okay, our next question. Are there any methods for better ensuring long-term contact between the anchor bolt nuts and base plates? Is utilizing double nuts or lock washers effective?
Yeah, using double nuts, it can be effective. I have seen that used in previous applications. Generally, we don't recommend lock washers just because they're typically not properly sized. But double nuts can be effective, but that assumes that you have sufficient thread length extending above the existing nut that you can put a lock nut in place. But generally, if you tighten the nut properly, it should not loosen over time.
Okay, this is a question for Leah, specifically about the last slide in the first section. How were the repair bolts installed?
Yeah, that's a good question. So if you remember the image, there was a large handhole cover or handhole, and so essentially a handhole is the access hole that provides you access to the electrical wiring, and the handhole is actually where they were able to provide access in order to get to the inside to install the other side of those bolts. So if it's a small pole, it may not be enough area, but for those high mass lighting poles, sometimes it's a larger area and you have access to get inside the pole.
Okay, our next question. Either during in-depth or routine inspections, do you take some UT thickness readings, even if corrosion is not evident on the outside of the pole, to verify corrosion is not occurring on the interior of the pole?
Yes, I can take that one. We always... Go ahead, Leah.
No, that's fine. You said exactly what I was going to say. We almost always will take some level of thickness readings. Just in the event, like I said, it'll be surprising sometimes that there is corrosion from the inside out, and it just gives us a good gauge of, is there section loss, and then we usually will take a measurement away from the base of the pole to get ourselves a baseline. So we can do a quick math on site that says if there's been 5%, 10%, 15% section loss, to give us, an understanding of how the pole is doing. So yes, we usually always consider UT thicknesses.
All right, our next question. What are the criteria for a properly tightened anchor bolt nut? Are anchor bolts tensioned with similar methods used for structural bolts, such as turn of nut, torque, or DTI washers? Are double top nuts ever used to prevent loosening?
Yes, so AASHTO does provide provisions for tightening of the nut, and it is the turn of the nut method, whereby you tighten the nut up to the point where it's snug tight. and then you turn it a certain fraction of one full revolution beyond snug tight, and that is based off the diameter of the anchor bolt, that fraction, as well as the material of the anchor rod itself. So, and then, yes, I think we already touched on double nuts can be effective if you have sufficient thread length.
Okay, our next question. I'm curious what new challenges or issues you're seeing with the advent of LED for site lights.
So I guess it's not necessarily an issue. Go ahead, Noah. Sorry.
Yeah, I think as Leah was going to say, it's usually we're seeing those LED lights have a reduced load on the light pole. So generally, that's a good thing. And they, are associated with lower energy consumption. So it's kind of a win-win-win. But it is, like I mentioned, it is important to have your poles evaluated when you plan to have those lights replaced, just to make sure that there's no other conditions going on.
Okay, our next question. Is bolt bending a concern if the anchor bolt sticks up too high?
Go ahead, Leah.
Yeah, that's a good question. And I'm actually going to directly quote AASHTO here. So for essentially, not really. Evidence that, or data has proven that bending of the bolt isn't usually a primary concern, especially if I think it says the top of the foundation is less than or equal to 1 bolt diameter from the other nut. So my answer to that is not really.
Okay, our next question. Both of you talked about corrosion found on the inside of poles. When found early on with minimal section loss, what work can be done to prevent advancement of the corrosion?
Yeah, that's a good
so
question.
generally there.
Go ahead, Noah.
Generally there, you're going to want to make sure that there's no debris within the pole that could be trapping moisture and accelerating that corrosion. If the corrosion is on the exterior, making sure that your coatings are intact and that the pole is well protected. If the corrosion is primarily on the inside, you want to make sure that there's no source of water getting in from up above that can accelerate that corrosion.
Okay, how do you look inside the pole?
Like I said earlier, there's a handhole cover that has a little cover on it, so you can take that off, usually with a little screw, and that'll give you access to the pole. It may not be of large size, but usually you can stick a borescope or a flashlight in there just to get a feel for what's going on inside.
Okay. Is it common for state DOTs to require fatigue loading requirements for poles less than 55 feet, even though AASHTO LTS does not require it?
Go ahead, Noel.
Yeah, I mean, I'm sorry, can you repeat that question, Liz?
Yes. Is it common for state DOTs to require fatigue loading requirements for poles less than 55 feet, even though AASHTO LTS does not require it?
No, based on my experience, AASHTO or state DOTs typically follow AASHTO recommendations and do not require fatigue loading for poles less than 55 feet because it's not required by AASHTO.
Okay. This person is curious about why loose bolts often indicate a cracked anchor rod.
I mean, yeah, if your nuts are loose, particularly if you have more than one loose nut, that pole can rock, and then those dynamic loads are much higher than what that bolt would experience if that nut were tight. So, as the rocking occurs, it impacts the underside of the nut, which can create a much higher load. And that's why you typically see cracked anchors at where there are loose nuts present.
All right, this will be our last question. Is there a recommended inspection cycle for poles, every 2 years or 5 years or 10 years?
Yeah, that's a good question. And the answer is it depends, unfortunately. So I think the biggest thing is to just get that baseline, get that initial inspection done. And that'll give us an understanding of what is the condition of the poles right now. Therefore, we can better estimate when and how often they should be inspected. I've done some where we say, oh, it's probably 3 to 5 years is adequate. Some I've started to say every year at this point because there's some advanced corrosion and we're keeping an eye on the corrosion and potential for cracking. So unfortunately it depends, but I think it's really about getting that baseline done and then projecting from there.
Great. Thank you, Leah, and thank you, Noah, for the great presentation, and thank you all for joining us today. We hope it's been educational. If you have any questions about today's presentation, please don't hesitate to reach out to Leah or Noah. They'd be happy to chat with you. And if you have any questions about WJE webinars, please reach out to me, Liz Pemper at lpemper@wje.com. So again, thank you so much for your time, and we hope you have a great rest of the day.